Every vibration textbook explains modal analysis, eigenvalue problems, and mode shapes. But can you explain what the mode physically is? Many engineers can't. In multi-degree of freedom systems, direct time-domain thinking becomes impractical very quickly. When such a system is excited, all coordinates move simultaneously, and the resulting motion appears complex and difficult to interpret. Modal analysis offers a different perspective. Instead of focusing on individual coordinates, we focus on the natural vibration behavior of the system itself. The core idea of modal analysis is simple. A mechanical system does not vibrate arbitrarily. It prefers to vibrate in specific, characteristic patterns, which we call modes. Each mode corresponds to one eigenfrequency and one mode shape. At the given eigenfrequency, all parts of the system move in a coordinated way, sometimes roughly in phase, sometimes against each other, leading to internal deformation. These coordinated motion patterns are system properties and represent distinct ways in which the system stores and exchanges kinetic and potential energy. It is important to clarify what the mode actually is. A mode is not the motion of a single mass or component. A mode is a coordinated motion of all masses in the system. Every degree of freedom participates in a mode, but with different amplitudes and sometimes even different directions. The mode shape describes how all parts of the system move relative to each other when vibrating at the specific eigenfrequency. A useful way to think about this is that a mode is a system property, not a component property. The same idea applies to eigenfrequencies. Eigenfrequencies do not come from the excitation. They belong to the system itself. Even without any external force, if the system is disturbed and released, it will naturally vibrate at its eigenfrequencies. This concept should already feel familiar from the single degree of freedom oscillator. The difference now is simply that the multi-degree of freedom system has several natural eigenfrequencies instead of just one. If you want to learn how to apply modal analysis like a professional engineer on real-world engineering tasks, check out the online course on vibration analysis with free chapters and guided step-by-step problem solving. Link is in the description. In real applications, systems are not excited at a single eigenfrequency, but by general, time-varying inputs, and the resulting motion can appear complex. Modal analysis shows that this motion can always be interpreted as a combination of the system's modes. Each mode contributes its own vibration pattern with a certain weight, and the total response is obtained by superposing these contributions. An intuitive analogy is color mixing. Complex motion arises from combination of a limited number of basic patterns. A crucial consequence of this view is that each mode can be treated independently. Each mode vibrates at its own eigenfrequency and does not exchange energy with other modes, behaving like an independent vibration mechanism. This does not mean the system is physically split, but that the motion can be decomposed into independent patterns, which makes complex vibration analysis manageable. In practice, not all modes are equally important. The lowest modes usually dominate the system response. There are clear physical reasons for this. Low-frequency modes involve large, global motions of the structure. They require less energy to be excited, and most real excitations contain more energy at low frequencies. High-frequent modes tend to be more localized and require higher excitation frequencies to become relevant. As a result, many engineering problems can be understood by considering only the first few modes. This is not the convenient shortcut, but the physically justified simplification. understanding modes and eigenfrequencies has very direct practical consequences. In vibration control, vibration problems are almost always linked to specific modes. Once the critical mode is identified, countermeasures such as damping or stiffness changes can be applied where the mode has a large motion. Modal analysis also allows engineers to avoid resonance by identifying critical eigenfrequencies early in the design process and enables efficient modeling by focusing on dominant modes instead of every individual coordinate. In the following chapters, we will learn how to systematically analyze the modes of a mechanical system, how to determine their eigenfrequencies and mode shapes, and how to apply these concepts to interesting and realistic engineering problems from practice.